So for our second talk in the morning, we have Professor Maryam Fazel from University of Washington come here today. Maryam is an accomplished optimization researcher, and she's currently leading the IFTS Institute, which is a Triport's Phase 2 Institute, collaboration of few different universities. Maryam, the floor is yours.
Thank you very much. Thanks to the organizers for a great event and for inviting me. So today I'll talk about flat minima and generalization with examples from matrix low-rank matrix recovery problems and some small neural networks. And this is joint work with my colleagues at University of Washington, Dima Drusviatsky, Zahid Harshawi, and also the main author is Lijun Ding, who is here at UC San Diego in the math department. I don't see him now, but he was around yesterday, so hopefully he will come back. If you have questions about the talk, he's really the best person to talk to. Okay. Oops. Ah, there we go. Yeah, so the talk is really one of these big questions about neural networks and deep learning that still remains poorly understood is why they generalize, when they generalize, how they generalize, all of those. So, and if we do have a nice theory for generalization eventually, that would be very helpful because it will allow us to, first of all, think better about designing the models like architectures. What is the role of architecture in generalization? What is the role of the training algorithms? And then also we can better evaluate these models. In particular, we would like to understand the roles, as I was saying, of different parts of the training pipeline. So what is the role of overparameterization? That is the size, the scale of the large models. How much does scaling matter? That's the big deal nowadays. How much does the choice of algorithm in the training matter? And how much does the geometry of the loss landscape matter? And what role does it play? The geometry of loss landscape, as you will see, is actually the topic of this talk. And it depends on so many things, the architecture, the number of parameters, etc. So it's the full complexity of how the loss function depends on all of your parameters. What's the role of the geometry or the shape of the loss? So yeah, in this talk, we will focus on the overparameterized learning regime, and we will try to understand generalization and its relation to flat minima in the loss landscape. So minima, local minima that have a flat shape. We will define it later. We will theoretically characterize flatness. We'll give a definition that works for our case studies. And we prove that for our case studies, flat minima generalize, provably, in the statistical settings that we consider that are similar to low-rank matrix recovery settings, if you're familiar with those topics. So in particular, our case studies are the following. All of them are, in a sense, a two-layer test case, but there are actually different problems that come up in different fields and applications. One is matrix sensing, or otherwise known as low-rank matrix recovery, matrix completion, a two-layer neural network problem. So these are several things we will mention in the talk, for which we show flatness results in generalization. But the result is also true for a whole bunch of other problems, including of similar kind, like phase retrieval, bilinear matrix sensing, robust principal component analysis, etc., low-rank plus sparse fitting. Yeah, so it's true for all of those. And we will also comment on the relation between flatness and some other properties and the interesting questions about the role of depth. So, okay, so this is very familiar with for audience here, so I won't spend too much time on it. But in modern deep learning, the training problem is looks like this. So you want to minimize a loss function, which is a summation of individual losses on all your data points. So here, yi is the label, xi is the feature of ith data point, and this h theta is capturing all your whole neural network. Thetas are all the parameters, and you just want to do a good fit by optimizing over the thetas, which are the parameters. So the number of parameters is d, the number of data points here is n, and we call these roughly overparameterized when the number of parameters is much bigger than the number of data samples. And thanks to work done at UCSD, so this is actually copied from a cartoon that is copied from a paper by Misha et al. So in 2018, they describe this double descent phenomenon. So when you're training a neural network or large models, on the vertical axis, this is the test error. And on the horizontal axis is some notion of capacity of hypothesis class, which in our case is just number of parameters theta. And in training, what people observed was that you first in the low, like under-parameterized, or when you have no low number of parameters, you see the typical overfitting behavior of first, the error goes down, and then it goes up. So this is the test error, and goes up. And somewhere around the threshold that is called an interpolation threshold, where your training loss actually goes to 0, then your test loss after that starts to decrease again. And sometimes this optimal, the value that it can achieve can be even lower than the best that could have been achieved in the under-parameterized regime. So being in over-parameterized regime is actually good, it turns out. So based on this, that's also called benign overfitting, and there's a lot of literature on it. We won't go into it. But it brings up the question of when you have overparameterization, you have many choices of theta that perfectly fit all your data points. So many zero-loss solutions. And then the question is, some of these zero-loss solutions in practice work well, meaning they generalize very well on new data, on seen data, but some don't. So what's going on? Why do some of these zero-loss solutions or networks trained up to zero-loss generalize well and others do not? So from this simple beginning observation, we can see that the value of training loss alone is not good enough. All of these have training loss 0, but some are not good. So it's not enough to just look at training loss. What are other properties that could predict generalization? When you are training, maybe you want to get a sense of, am I actually getting a good model? So this topic has been studied from several different points of view. One is explicit or implicit regularization. So of course, regularization plays an important role in picking which one among all the solutions you will converge to. And there's a long line of work in this topic, starting from the work of Surya Gunasekar, and then others that have looked into, for example, gradient descent and stochastic gradient descent, and what are the implicit regularizers that arise when you apply these algorithms to these kinds of landscapes. But the second one is, well, maybe there are some properties just of the loss landscape that matter. And in particular, the flatness. The flatter regions of loss seem to be better. So the topic of this talk is about the second one. We will not discuss the first one. So we will not discuss training algorithms. We will only ask the question of, can we actually show that the shape of the landscape has an effect on generalization? So flatness involves both the loss function, the choice of the little l, and the choice of h theta, of course. So it's also architecture, both loss function and architecture. How do those play a role? Now, flat landscape is a really old idea, actually. And the question is whether should we revisit this old idea? The old observation going back to 96, a paper of Hochreiter and Schmidt-Huber is, and actually I have a picture of that paper here, so 96. They actually observed in very small neural networks at the time, it's like only 3-4 layers and so on. They did draw the loss landscape of these small neural networks and observed that actually flat regions seem to be generalizing much better. So trained to get to the flat regions of the loss. So old observation that flat landscape of the loss correlates with generalization. Right. This idea has been revisited recently quite a bit. There's just a couple of examples of papers that revisited the idea. Entropy SGD looked at biasing gradient descent into wide valleys, like take SGD and add some kind of entropy regularization in order to get to wider regions. So this is from 2017. And then sharpness-aware minimization, which is very popular in practice for neural network training, that came out of Google in 21, also really relies on this idea that if we can try to bias the iterates to go towards flatter regions, and in practice, it works really well. So there is something, it seems, about flatness. Some more empirical evidence about why flatness is good. So these are from 2 papers from Tom Goldstein's group at University of Maryland, in which they did careful experiments and tried to visualize the loss landscape of training neural networks. So these examples are a 6-layer neural network, and it's a simple classifier And the data, the example that they're looking at here is the Swiss roll data. So you have the red points and the blue points. And on the left, you see that the classifier that was trained on this data is a nice classifier. It separates all the blue points and red points correctly. So it is a zero loss solution. So what we are showing, by the way, here is in the data space, and we are showing the decision boundary of the classifier on data. We see that it's correct, of course, it's zero loss, but also it has a pretty good margin, like data points are not too close to the boundary. This solution corresponds to, if you look in the training loss landscape, corresponds to a minima that looks like this. It's pretty flat looking. Now, they actually were saying that many algorithms do happen to find the flatter solutions easier than the sharp ones. So they actually designed some ways to push the algorithm to go to a sharp solution. And then they observed that, for example, you can get a solution on the landscape that looks like this. It's pretty sharp. And the corresponding classifier, if you again look at the space of data points, looks like this. It's like a crazy classifier. Even though it is zero loss, it's classifying all the red points and blue points correctly. It is really, really fragile, clearly. So a tiny bit of change in any of the data points is going to make it misclassify. And very clear that it's not robust to any perturbation in the data space, not in the weight of the model space, but it's also not robust in the weight space. But the end result in the data space is not generalizing. So this is evidence that, see, flat model generalizes well. Sharp model is terrible for generalization. So there is something going on with the shape of the landscape, even though both are zero loss solutions. Another observation that papers of Tom Goldstein had was that in general, in the loss landscapes of these networks that they studied, there is a larger volume around flat minima. And that's maybe why in their observation that many common algorithms actually tend to go to the flatter regions. So there's like some volume argument. But for us, this is encouraging that, okay, there seems to be something about flatness that is helpful. So we want to see, can we prove anything? And another thing is, well, how do we even measure flatness? What's a good measure? What's a good way to think about it? Since many of the previous works kind of talk about it in a very intuitive way, flat region, but they don't actually define and measure it. But there are ways to. So we are going to look at a class of problems to study this phenomenon. These are overparameterized low-rank matrix recovery problems. And there's a bunch of them. In this talk, I'll look at two of them. The matrix recovery one is the simplest case. Then we will also look at a one hidden layer neural network with quadratic activation as an example of a small toy neural network. And they proved that for all of these, flat minima exactly recover a ground truth generative model under certain statistical assumptions that will look familiar when we get there, which means they generalize, perfectly generalize, because they recover the generative model that generates the data. So any other data point coming from that will be handled correctly. You'll get the correct labels. So, okay, matrix sensing problem, just a quick reminder. Probably most people here are already familiar. The problem of matrix sensing is an older problem. This is not about neural networks. It's just about, I need to find a low-rank matrix of size d by d, given linear measurements or linear constraints on that matrix. So M sharp is the matrix that is low rank that we want to find. We have M linear measurements. Here we define them as their inner products with these sensing matrices or measurement matrices A1 through AM. We stack them all in a vector and we use this notation script A. Script A is a linear function of the matrix X. Here, the model that we are trying to recover has rank R sharp, which is much smaller than the size of the matrix. And so this is a classical problem by now. One convex relaxation that works well is using the matrix nuclear norm. And nuclear norm is the sum of the singular values of the matrix. It can be seen as a proxy for rank, therefore a notion of complexity of the underlying matrix. And that's well understood by now. It's explicit regularization using nuclear norm. It's well understood when and how this solution of this is the underlying low rank matrix. And it has a lot of its own applications. You know, it already has been studied quite a bit. It's a legitimate problem of its own interest. However, in this talk, we are not looking at these applications. We are actually, in a more recent trend, we are looking at a non-convex parameterization of this low rank recovery problem as a simple model for neural networks. So we are going to deliberately write it as a nonconvex problem because then it would mimic the behavior of a two-layer neural network. And we'll make that connection to neural networks a little bit later. Okay, so this is the problem again. Let's write it in terms of a non-convex parameterization of the matrix X. Just write down the matrix X as a left factor times an right factor, L R transpose. And we are going to take the measurement constraints, put it in the loss function, define a loss function to be L2 norm squared of the violations of those measurements. And the optimization is now over L and R. Each of those are a matrix of size D by K. D is the size of the original matrix M, but K is another parameter that can also be as large as D. So, and B equals, the vector B is just these measurements as we had before, corresponding to the correct underlying ground truth M star. Now, overparameterization here is captured by this factor K. K is chosen to be much bigger than R sharp. So we are not factorizing this in a small size efficient way. We are actually taking product of two bigger than needed matrices. So K can be seen as overparameterization. Now, how do you think of this problem as a neural network or data fitting type of problem? You can think of L and R as model parameters of, let's say, layer 1 and layer 2, two-layer model. AI and BI are the data, so AIs are the features, BI are the labels. M sharp is the generative model, is the underlying low-rank model that generates these data, therefore data fit that M sharp. And so you can think of it as a two-layer linear network where L and R are layer weights. And so this model has been studied a lot, especially to study the role of the algorithms and how would algorithms apply to this non-convex problem work. And there's a long line of work on that. When do they converge, etc. Now, we are interested in flatness. So let's actually define flatness for this particular problem. First, we look at writing down a set that is the set of all interpolating solutions, which means everything that makes the loss exactly zero, which is all L and R such that A LR transpose equals B. Define that set as S. Now, we are going to look at flatness. What's the reasonable notion of flatness? As we have seen in other talks also, it has to do with the Hessian. If the function is twice differentiable, let's look at the Hessian. But the Hessian is a matrix. So what measure of that captures flatness? It could be the trace. It could be the condition number. It could be just the maximum eigenvalue of the Hessian. All of these are reasonable choices in some sense. We are going to look at the trace of the Hessian because it's the easiest to analyze. Really, we just picked it because it was easy to work with. It turned out it worked really well in all the examples we studied, luckily. So why do we look at Hessian, by the way? And you can think of it as in the space of functions of two matrices L and R, the Hessian of F is actually a complicated 4-tensor type thing. You can flatten it into matrix, but it is a second derivative of the function F evaluated at L and R in directions U and V. So if you perturb your L and R by matrix amounts U and V, this would be the value of the perturbed function. Why am I writing this is almost equal? Because you can write the Taylor expansion. The first term, the linear term, is going to be 0 on this set S because the loss function is 0. And so you basically are approximating your value of F as a constant plus the Hessian, or the second order term of the Taylor approximation, not just the Hessian times the perturbations. So as flatness measure, we use trace of Hessian. This actually has been used before. It's kind of the most natural notion. It's the sum of the eigenvalues of the Hessian. It has a nice meaning that because it's the sum of the eigenvalues, it's actually measuring average notion of flatness. You can also interpret it as follows. If you take the points L and R and perturb them by U and V, where U and V are matrices that are random, let's say they're Gaussian, zero mean with identity covariance, then the expectation of how much your function value changes is exactly this trace of the Hessian. So on expectation, if you are moving around, this is how much change you will see. So it's an average measure of curvature. You might think average may not be good enough in all applications. In these cases, it worked perfectly. So again, we were lucky and it's easier to analyze. Let's take a look at a simple case as a warm-up. If my map script A, like the linear measurement map, was just identity, the problem simplifies quite a bit. Let's write that down. Then it looks like this: minimize over ln(r) of Frobenius norm of LR transpose minus M sharp squared. Right, the A was identity, so it went away. Now this problem is a little less interesting in the sense of matrix recovery, because every zero loss solution here is recovering M star automatically. But still, looking at the flatness of this problem will be insightful. Again, let's write down the Hessian, or the second order Taylor expansion around LR, and LR that we pick belong to S. So this is the set of interpolating solutions. Loss is 0 in the points that we are interested in. So in those points, that loss is 0. The second order expansion looks like this. This is the first term, but this is 0. So you're left with a term like this, Frobenius norm of some function of matrices, like that. Let's look at a very, very simple special case, a scalar case of this problem. In the scalar case, the ln(r) are just like little x and y, or they are scalars, and M sharp, let's say, is just number 1. And you're looking at this loss function over here, xy minus 1 squared. Let's plot the solutions. So the solutions will be y equals 1 over x and minus that. So this yellow curve and this yellow curve are the zero loss solutions for this particular loss function. And in this picture, we are using the heat map to show the width of the, or the size of the second derivative around each point. And you can see the width of the blue region around this curve tells you whether you are in a sharper part of this valley of zero loss solutions or a flatter part. And just visually, you can see the flattest part is this part. That's the flattest. Or this, it's symmetric. So 1, 1 and -1, -1 are the flat solutions. These, by flat, I mean, in this talk, I mean the flattest, the one with the minimum trace of Hessian. But so it's interesting that we can see, yeah, as you expect, or may not expect, there's also other results that people suspected that balancedness of the factors is an important thing. And here they overlap, actually. So balancedness means that x and y are not too different in scale. And indeed, you can see the ones that have the biggest width are the most balanced, as well as being minimum L2 norm. So these 2 points also have the property of being closest to the origin, the 1, 1 and -1, -1. So in this special case, we can actually prove that when A is identity, the flatness corresponds exactly to norm minimal and balancedness. But this is not true when your A is not identity. Question?
Is this a visualization of this
Yeah, that's right. That's right. Yeah, it's the heat map that shows the second order expansion. So therefore, you can see what the curvature is around zero loss solutions. The zero loss solutions are those yellow curves. Question?
I have a confusion regarding what you are trying to show. Suppose for the matrix sensing problem, to recover the ground truth, you know that you need this many number of measurements, right? So, or like any of this type of problems.
Okay.
So to recover ground truth, you need this many, but you were saying it is overparameterized, so you have less number of such measurements, right?
Actually, we will get there. We will get to the number of measurements here.
Right.
Yeah.
Well, like, okay, so my confusion.
So I will show that.
If you are actually doing less and then just looking for flat, how do you go back and recover ground truth? I mean, isn't that breaking some?
So we will actually get there. Yeah. Thank you. Good question. Yeah, so far it's not yet about the number of measurements, but that's the next, in a couple of slides, we'll get to it. Okay, so flat solutions for this problem, how do we define them? Let's just minimize the flatness measure that we defined, which is trace of Hessian. So minimum trace of Hessian over L&R of this, right? And so this is pretty complicated function of L&R. It's quadratic in L&R. Subject to, you also want to interpolate. So we put the interpolation as constraint. This is also quadratic in an ln(r). So nasty non-convex problem, pretty bad. But turns out we can massage this problem and actually has some very interesting properties. One lemma is that a flat solution, the minimizer of the Hessian trace, actually corresponds to the minimizers of this problem. This is not too surprising, although it has some interesting interpretation, because this problem has the loss function or cost function is the nuclear norm of a weighted version of matrix X. By the way, X is LR transpose. So I'm going back to put it together in a matrix X. So this is minimization over X of nuclear norm of some weighted version of X, where these weights D1 and D2 are actually data-dependent scaling matrices that look like this. You can actually think of them as some kind of preconditioner. It does look like, right? So you take the measurements AI, and this one is the right version and left version of trying to scale to make everything isotropic. And we have subject to Ax equal to B. That's just the interpolation condition. And we need to also impose rank X is less than or equal to K. So far, this is still not convex because of the rank constraints. But we can further show that if you relax the flatness problem, that problem, by dropping the rank constraint, then you get a convex problem. So let's observe this is convex because it is nuclear norm of a weighted version of X. It's a convex function, and this is a convex constraint in X, convex in X, not L and R. But we can prove that under standard statistical assumptions, which are assumptions on the measurement map A, which it has to be random enough, which, for example, it can be the restricted isometry property or other similar kinds of properties that are familiar in the line of study on low-rank matrix recovery. Under those assumptions, which in the case of, like, for example, neural network, translates into data being random enough, feature maps especially being random enough, then the flat solution, so the solution of this relaxed optimization problem, which is a convex problem, exactly recovers the correct M sharp. So the strategy to show this is first show that M sharp is the unique solution of the convex optimization problem. And this doesn't quite follow from already known results on nuclear norm. And we need to actually do a new derivation because of these rescaling matrices. Because the rescaling matrices are actually data dependent. So your objective and your constraints both are data dependent. The AIs are showing up in both. Remember that D1 and D2 also have AIs in them. So we needed to do a little bit further analysis. It doesn't follow from the known ones. But then you can put it together and get things like this. Actually, that hopefully answers Arya's question. So if you actually look at so this is again the measurement map A of X was the inner product between the X and all of the measurement matrices A1 through AM. If the A1 through AM are, for example, coming from the Gaussian distribution, meaning every entry in each of these matrices is an IID standard Gaussian, or if they come from a Gaussian bilinear distribution, which means these AIs are rank 1 matrices where the vectors come from a normal distribution. And there's a whole bunch of other these families also well studied in low rank recovery. For these, we can show something about the flatness recovery, which is as follows. If the number of measurements is on the order of, so this is hiding, this notation is hiding constants, is on the order of the rank R sharp times the dimension D, which is, by the way, the same number of measurements that you would need for nuclear norm recovery of a low rank matrix. Then with probability, that's also very similar to nuclear norm recovery, probability that goes to 1 exponentially as the number of measurements grow, then any flat solution, any solution to minimize the trace of the Hessian problem actually correctly recovers M sharp. And we also have some additional results, which is something about norm minimality and balancedness of flat solutions. So for this problem, which covers matrix sensing and bilinear sensing, we can show that the L2 norm of LNR is also bounded by the nuclear norm of the true solution. And so the norm is smaller than something. There's a bound on the norm. So there's a relation to norm minimality, as well as balancedness. So the balancedness of the solution, which is the difference between L transpose L minus R transpose R, this is known as balancedness. We can think of it as when we had the scalar version, when xy minus 1 squared was the function, then x and y being close to each other means balancedness. So this is a matrix version of thinking of balancedness. Some papers have studied this as a notion. We can also show that the balancedness is also bounded by the nuclear norm of the solution. But the main result here is that recovery happens, the flattest solution recovers the original low-rank matrix with the similar number of measurements on the same order as the nuclear norm recovery, which is known information theoretically to be within log factor. Actually, for this, not even log factor. It's within constant. So flat solutions are basically as good as nuclear norm. Here's another case study. So that was a problem on matrix sensing, but this one is a little bit closer to actual neural networks. It's a very toy version of a neural network. So this is a single hidden layer neural net with quadratic activation. This is actually a model that was developed in earlier papers, Matthew's paper and others. So we just use the same development of the model from these references. In this case, we have a data X in RD, and we have the output or response or label corresponding to the data, that's Y of X. And with the teacher network, so there's an underlying neural network that, let's say, generates your data. This teacher network is defined to be like this. So it depends on this ground truth matrix U sharp, and of course, the data point you're putting in. And it returns the label that is some V transpose Q of U sharp transpose X. This Q function here is an activation function. This U sharp is a matrix of dimension D times R sharp. So this is a matrix with a smaller dimension. So it's a dimensionality reduction type of thing. It reduces, the internal dimension is R sharp. V is of size R sharp, and we assume that it has some number of positive entries and some number of negative entries, could also have 0 entries. And Q is the activation function. In this very simple example, we are taking it to be a quadratic function, entry-wise square. Yeah, one can try to think of other activations as well, but this is, again, the easiest to analyze. Okay, so this is the setup. We have a teacher neural network that generates data. And you can see the key thing is that if we want to have a student network to reproduce the results of the teacher network, we need to learn that U sharp. It is also known as, by the way, multi-index model over here. And this is a combination, linear combination of the multi-index models. Okay, so here's the prediction. The student neural network will take any U and a data point X, and will give you this. So the things to be trained are the matrix U and the little u. However, it turns out the little u without loss of generality can actually be fixed to something that has a bunch of positive or +1 entries, -1 entries, as long as these K1 and K2, the number of plus and minuses in this U are chosen to be bigger than the original R1 and R2. So the U is not really a training variable. The training variable becomes just this matrix U. Okay, what is the overparameterized training problem? It looks like this. We want to minimize function of U. U was a matrix D by K. That is the sum of the squares of the errors on all the data points. And for this problem, we can actually calculate the flattest would be trace of the Hessian of this F, but we can actually calculate this and simplify this problem of finding the flattest solution. And it's kind of nice. So this is the problem again. This is how we reduce it. You can actually split this matrix into a U1 and U2 according to the signs of the plus and minuses of the U's. And you can write the whole objective as this. So you get A acting on U1, U1 transpose minus U2, U2 transpose minus M sharp, L2 squared. So now this is kind of nice because it looks like matrix factorization again. We can actually kind of use some of the results we had earlier. Here, the AIs, by the way, are XI, XI transpose, outer product of the data features. And M sharp is U sharp. U sharp transpose is a symmetric matrix with a diag of V in the middle. The V was the original vector in the teacher network. In particular, this model reduces to phase retrieval and covariance matrix estimation in special cases, so it covers those. Now, what can we say about this flat solution for this problem? We can prove that if the number of measurements is again on the order of R sharp times D, so rank times the dimension, then again with an exponential probability that goes exponentially to 1, Any flat solution, UF, achieves basically zero generalization error because on average over data points that are random Gaussian zero mean identity covariance, the predicted label and the true label in expectation have zero error. So that's the perfect generalization. So we can also try this numerically for some examples. And in fact, what we did was we plotted how well would flat solutions recover in different settings and compared it to how well does nuclear norm minimization, the convex version, not the non-convex LNR version, recover. And we get things like this. So this column on the left is for matrix sensing problem, then matrix completion problem, which I didn't talk about, and then the neural network with quadratic activation problem. And the top ones are the convex relaxation of the scaled trace minimization, which is the problem that I talked about, which is exactly finding the flattest solution. It's a relaxation, but we showed it was exact. So it's exactly finding the flattest solution. And the second row is the nuclear norm minimization. And we can see they're very similar. They're not exactly the same. In fact, flatness seems to be slightly better. We can't prove it, order-wise they're exactly the same, but it seems constant-wise it's a little bit improved. But more or less, it's working as we expect. So, yeah. Oh, yeah, I didn't explain. Sorry, I didn't explain. So the white is perfectly recovering, black is not recovering, and this is showing, this axis is the number of measurements or number M, number of the constraints. And this axis is the D, the dimension of the matrix. So measurements and the dimension, you get this two-dimensional plane. Every pixel here is a combination of M and D. And then to simulate it, for every corner here, you generate like 10 cases and then check which percentage recovered or didn't recover and color it white if it perfectly recovered and black if it didn't. And some things are gray, not too many, but for example, here in the boundary, you see gray. So then sometimes it recovers and sometimes not. Yes, exactly. When you recover the correct underlying low-rank matrix, it means you recovered the generative model that generates your data, therefore you generalize perfectly. Yeah, that's the relation. So everything we said was for a two-layer type problem. So a natural question is what happens when you have more depth, more than 2 layers. And so the summary is that question is not answered yet. Might be too hard to answer. But we can actually make some observations in a special case. And it's kind of interesting, this special case is a bit of a negative result. So consider the problem in which you have a vector X that you want to recover, vector X here. So this is really a least squares problem. It's AX minus B L2 squared. But take your vector X and write it as a Hadamard product of a bunch of other vectors, that's entry-wise products. So V1 through Vk is like a k-layer model for this X. And now we are going to minimize over V1 through Vk. Each of them are in RD. So, instead of low rank solution, here we look for an X underlying X ground truth that is sparse, R-sharp sparse. So basically, it's the rank problem that reduces to sparsity problem when you go from matrix case to the vector case. Now, what does a flat solution look like for this problem? So we can write down the flatness problem, minimize trace of the Hessian. The Hessian here can be nicely calculated in closed form. And you can actually then simplify the problem. So simplify this flatness problem. It will be equivalent to this, going back to X, from V going back to the space of X. There are some scaling factors that show up. I haven't written explicitly what they look like, but that depends on the A and B. And then you have absolute value of each xi to some power, 2 minus 2 over k, subject to x equal to b. So then this we can interpret, and k is the number of layers in this example. What is the relation between this example and the previous ones? You can think of as we had product of 2 matrices. Now you have product of k matrices, but all of your matrices are diagonal. that reduces to this problem. So the way to reduce a matrix problem to vector one is you make the matrix diagonal, right? So that's what we're doing. And then the interpretation is this. If K was 2, you get a 1 norm minimization or weighted L1 norm minimization, which is good. It recovers the sparse vector. If K is larger, in particular, if K goes to infinity, things actually don't look good because you get the weighted L2 norm. And that doesn't recover a sparse solution. So it does seem like in the case of at least diagonal layers, having many layers doesn't help.
One case with two. Okay. In case with two, you get a one.
That's right.
So what happens when K equals to 1? You just have one diagonal.
Yeah, K equals to 1, then the power will be 0. So this will be a constant. So then this won't do anything. Yeah. I mean,
Not a constant, it's the number of non-zero elements.
yeah, actually, that's true. As K approaches 1, it's approaching cardinality in some sense. Yeah, that's true. I actually didn't think of 1, but
Yeah, but K equal to 1 is the original parameter.
It's original parameter.
It's a convex parameter.
yeah.
Without this.
So, like, what you were saying that if you have a compressed sensing problem,
Uh-huh.
without knowing K, you can just solve it. And with
No.
just give the flat test solution, and is that going to be a sparse solution?
No, I don't think so. L1 came out when K is 2, and L1 is the one that
No, but
recovers.
like when you say K equals to 2, I mean, it's not solvable. Like you cannot do it.
K is smaller than 2.
K smaller than 2, it's not convex. Yeah. But so it's not very useful, right?
Yeah, I mean, but suppose you could, maybe you cannot solve it in real time, but it's still, is it the sparsity? You are getting back the sparse solution?
Actually, that's a good question. So, if you look at the trace of Hessian, or if you look at flatness for what, I mean, for, yeah, maybe you take cardinality problems, smooth it, and measure flatness. Does that help you? Can you say then the flattest is the zero norm solution? Yeah, maybe. Maybe it is implying something like that. Yeah. Yeah, interesting question. We were interested when we looked at this, we wanted to grow K because we wanted to look at more than 2 layers because we already had the perfect recovery of 2 layers. And it turns out, so exact recovery holds for K equals 2, but it gets bad when K goes to infinity. And experimentally, that also does work. So somehow, in the case of diagonal, in the case of vectors, more layers does not help. So that's an interesting observation. However, I want to point out there's some more recent work. So for example, this paper in Eurips of 2023 tried to show some results theoretically about a K-layer linear network, so product of K matrices that are not diagonal. So diagonal doesn't work, we know that. But the question is, what about if they're not diagonal? More complicated things can happen because your eigenvectors of these product matrices can align in different ways, and product can behave differently. So diagonal is too simple. But so they did show bounds for a general K-layer linear network in terms of the nuclear norm solution. But the bounds actually get worse with K. And it's unclear that, so for K very large, the bound becomes useless. But for maybe for small K and medium range K, they at least have some bounds that, so it shows approximate recovery. They do not show exact recovery. But it's interesting. So there is some work going on in the depth question of how do we understand the role of depth and flatness. And empirically, flat minima keep being observed to actually generalize well. As we can see, for example, the SAM algorithm, sharpness-aware minimization algorithm that tries to find, in some indirect way, tries to find flat solutions, is popular even for some foundation models. So interestingly, still in practice relevant for a large number of layers, but theoretical explanation is still open for K bigger than 2. Our work is just K equals 2. Okay, so to summarize, so we have shown that flat minima generalize for a family of overparameterized non-convex problems that are of the matrix factorization kind. And I want to point out that you can also handle noisy labels for the matrix sensing problem. Easy to extend the result, and recovery is then within the noise level, the recovery error within the noise level. And this is an appendix of our paper. We also, in our paper, look at the relationship between flatness and some other sort of regularizations that people have studied or used in practice. For example, its relation to norm minimality, which is basically called weight decay. So when people have L2 norm penalty on the weights, and its relations to balancedness. And these are equivalent exactly only when the map A was identity, and when A is not identity, they're not equivalent, but there's some potential bounds or one-way relations that can be shown. Some implications of understanding flatness is that, first, you can think of Hessian trace as a good regularizer. And indeed, it has to do with conditioning of your problem as well. And so you can think of ways to try to use Hessian trace as a regularizer. Of course, Hessian evaluation is hard, so maybe you want to do some kind of randomized method, etc., like Madden talked about yesterday. Potentially, it can be useful. Another message is that from algorithmic perspective, so far this talk did not say anything about training algorithms, but at least we now have a theoretical understanding of it's good to have methods that would bias iterates towards flat regions. So you may want to look for such methods or try to find ways to bias the iterates. So for example, the SAM algorithm tries to do that. And also that some things about landscape also that come up as a side result, which is the result that showed the flat solution is also nearly balanced somehow means that conditioning is also good. Like L and R are not very different in their values. So algorithms should be well behaved near flat solutions. But there are some things that are still open about this, about flatness. As I mentioned, one of them is the role of depth. And then another question that's open is flatness is good for generalization, as we saw, but it could be bad for convergence rate if you don't modify your first order algorithm appropriately. So maybe you want to trade these off. Simply because gradient methods, when the gradient is small, progress very slowly. And then what is the relevance to LLMs and foundation models? Empirically, it seems there is some relevance, but theoretically, we don't actually know. Is there any role of like attention architecture, attention models, and so on, transformer architecture, and flatness? That hasn't been studied either. So with that, I will just point out we have a paper. It's quite a long paper. So basically everything, almost everything I said is in that paper. And okay, I'll end here.